Like, as it is running now, do you think it's going to be an issue?
The music, I think, will.
Yeah, I think so too. Cool. All right.
There's an eraser next to that yellow binder to your left.
Thank you. Okay, if you guys were here last time, you might remember my 3 rules for electronics. Current flows from negative to positive, current flows into the pointy end, and the collector is connected to the load. And here's what I mean by that. If you've got, for example, an LED, that's the symbol for an LED, current would have to flow into the pointy end this way, so you would have to put negative down here and positive up here. And the collector is connected to the load, refers to transistors. We'll use that later on. The topic tonight is stepper motors. And how many people here have ever taken apart a stepper motor? Mysterious, isn't it? It just looks weird. It's this cylinder that's got bumpies on it, and that's about it. You wonder how the darn thing moves. Okay, let's start with 2 things. One is magnets, and we know a couple of things about magnets. They have north poles and south poles, and you can tell me what's going to happen here. What happens in this situation? They repel. Like poles repel, unlike poles attract. This is stuff you learned when you were 5, probably. And this is a coil. And any piece of wire that has more than 1 turn in it is a coil. So if I take a piece of wire and I put a turn in it, that's now a coil. If I put 1,000 turns in it, that would still be a coil. The properties would be the same. So this is a coil, and there's one thing that's very interesting about this coil, which is just a piece of wire. Because we've coiled it up, it now has the property to turn current into magnetic fields, or focus it into a magnetic field. So as an example, if I put positive here and negative here, current is going to flow into this wire. And because we have current flowing through a wire, moving current in a wire, you will get a magnetic field. 2 things I'd like to say about that right now, and I'll be using it over and over again. One is, you can do this. You can take your left hand, and for the coils of wire, if you put your finger in the direction of flow, that is to say, if I had a coil of wire that was like this, I would have current flowing this way. If I put my fingers pointing in the direction of flow on my left hand, the thumb would point to north. So I can't draw in 3D very well, but if you could imagine this coil being this way, my fingers would be pointing this way because the current's going into the board on the top, and this would be now the north end. This would be the south end. So every time you've got current flowing through a wire, you get a magnetic field. And you can tell which way it's going to be by putting your fingers, the left hand, into the way the current's going. That's not so important. The important thing is to know that you put current through a wire, a coil, and you get a magnetic field. It happens on wires as well. It's just not very focused. Coils allow you to focus that magnetic energy. The other thing I'd like to be using over and over again is this. If this thing has a magnetic field, I need to be able to tell you this. I can tell you it's got a north end by putting N, and a south end by putting S. How do I tell you it actually has a magnetic field when I'm drawing? This is what I'll do. That represents a magnetic field. Okay, that's the symbol I'll be using.
Is that the standard electronic notation, or is that Karl's special notation?
Actually, I haven't found any notation for showing a magnetic field. If this was a proper 3D board, it would go boom, boom, something. I don't know.
So the standard symbol more implies that there's a magnetic field.
Every textbook seems to have some different way of doing it. It all depends on the typesetter, I think. So anyhow, that's what I'm going to be using. Now, what's inside a stepper motor depends on a lot of different things. Just because there's so many different ways of making them. But what they all have in common is this characteristic. They don't go round and round. They go clunk, 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 clunk. They may sound and look different. They may be going zzz and look like they're moving smoothly, but they're actually going clunk, 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 clunk. Does anybody have a clock on the wall at home that goes tick, 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 tick? Y'all got one of those? Yeah. Well, if you take it apart to change the little battery, you might actually see this little wheel going click, click. It actually does a half a revolution each time. And that's a stepper motor. And the way those things work is quite interesting. They take a piece of metal and they just stamp out this piece of metal. They stamp a little hole in it here, and they stamp a hole in it here. They put some wire around it this way. And they can do two things to this wire. They could put positive here and negative here, or they could put negative here and positive here. What would that do, changing the polarity? Yeah?
Change the direction.
Change it the direction of
This different motor.
the magnetic field. You see, if I've got current going this way, from negative to positive, I can say, well, my fingers are going in the direction of flow. But if I turn it around, my fingers would be pointing this way, and my thumb would be pointing that way, to north. So not only can I make a magnetic field on a coil of wire, I can change the direction by changing the polarity. And that's the trick they use here. If they put positive here and negative on the other wire, I'm going to say, just arbitrarily choose, that this is going to be the north end, and this will be the south end. And if I change the polarity around, I'm going to have north here and south here. So this piece of wire, which is coiled up, and we put electricity through it, becomes an electromagnet. Sounds like something you'd use in Star Trek right next to the flux capacitor. This electromagnet, we can change the polarity on it, and we can change the polarity of the magnetic field, north on this end or north on that end. Now we'll leave that to the electronics, and we'll get to the electronics later on. Right now we're just focusing on the mechanics of it all. So you could actually make this work by taking a battery and putting it on this way, and then turning it around, putting it that way. You could make this thing rotate. What rotates? Well, what rotates is a little disc inside, which is on a pivot, so it would rotate round and round. And this little disc is made up of a magnet. And we have north on one side and south on the other. Now here's how it works. The electronics power up the electromagnetic coil so that we have north here and south here. So step one, we have north here and south here. What's going to happen is this little coil, this little magnet is going to go this way. Since north, whoops, sorry, I've got this backwards. Sorry, south, there we go, and north. Okay, since like poles repel and unlike poles, such as south and north, attract, the south is going to get attracted to the north. And what you're going to end up with is this. The south is going to turn so that we're here. Oops, wrong way. south, and the north is going to be on that side.
How do you control which way it turns when it goes?
Well, you may notice that I've started out with this thing at a little slant. Okay? And so it wouldn't go around the long way. It would
For
go.
the first one, but what about the second?
Oh, well, just hang on here.
Sorry.
Okay? So this is the first one. It just happened this way. You know, God said, let there be a little magnet, and it turned out to be on this polarity. Okay, so what's going to happen is from step 0 here, that's where we started from, to step 1, we now are in this position. And here's what we do next. We take the power away. So there's no more magnetic field. And now we answer your question. Now that there's no more magnetic field, you think this little guy would just kind of flop over from the weight of the minute hand or something. But what happens is, this is a sheet of metal, and it's got some residual magnetism. And because of that, this is not so much north anymore, and this is not so much south anymore. And what happens is, from the residual magnetism, even though we have no voltage, we have this happening. This little guy, because now this is a little bit south and this is a little, in other words, the magnetic field shifts, the flux shifts a bit. This guy droops. Essentially, he does this. You see, I was just kind of falling a little bit. Not so much falling, he gets twisted because this sheet metal has a little bit of residual magnetism. And now he's in the complementary position that we started from. And that's why he started that way. The residual magnetism from the previous energization. So, we're here, and we're going to change this now, the polarity, so that we got north here and south here. And so we just keep doing that. The electronics keep changing it. I'm not going to draw the whole thing because we've got a lot to cover tonight. But you can see how this works. And what's cool about this is, A, we have only one coil, and B, we have a motor that goes thunk, thunk, thunk. It's actually a 2-step per revolution motor. Right? It goes clunk and then clunk. So it's not exactly got fine resolution. You probably wouldn't want to make one of those stepper motors draw something because it wouldn't work so well. Clunk, clunk. That's about it. So it's simple, but it's not that practical. It's got great uses in electric clocks because you can gear it down so much. But here's something I'd like to point out about this simple magnetic device, is that we have a coil which has energy flowing in both directions. That is, sometimes I have positive here, and sometimes I have negative here. So my polarity is, oops, I have a bipolar coil. That is, sometimes current flows through this way, sometimes it flows the other way. We're going to be using that later on in more complicated motors. The other thing is, this little guy that rotates, he has a special name. Anybody? He rotates.
Rotator.
Rotator, close. Yes, very good. More beer for this man. The part that rotates is called the rotor. And the part that stays still is called the, now you can say it.
Stator.
Stator, yes. How could we make this more usable? That is to say, how could we get more steps per rotation, finer steps through this? Well, we could have more coils, and we could probably use more magnetic poles on the stator, or pardon me, on the rotor. Okay, let's do that. I'm going to make another one here. Now, if I've got this guy set up to rotate, I put a hole through this chunk of metal. You could see that if I had a magnetic field on here and a magnetic field on here, I wouldn't be able to turn this piece of metal, would I? Because these magnets, these electromagnets, would try to keep it steady. All right, if I put some more magnetic poles here, electromagnets, what I could do is this. I could turn these coils off and turn these coils on, and this guy would go kalunk. Question is, if he is really straight like I've drawn him, will he go this way or will he go this way? You don't know. What I've got here is actual coils, and I don't have a frame around it to create residual magnetism, so you're kind of stuck. It's not so useful. However, we can make it very useful by doing this. Instead of using a chunk of metal, we use a magnet, where we magnetize the chunk of metal. And now we can actually do something. We could have this here turned on. Now, since this end is permanently north, this is a permanent magnet, this electromagnet would have to be south. Very good. And this one would have to, of course, be north. Now, if I wanted this guy to go clockwise, I could do this. I could turn this off and turn this guy on south and this guy on north, and it would have no choice. It wouldn't be able to go this way, would it? It'd have to go that way. So now I can step and I can control the direction just by controlling what polarity I feed these guys, and that's the job of the electronics. We'll worry about that later on. So now we have a stepper motor. How many steps per revolution would this motor have? Well, we start here. That's 1, 2, 3, 4. This motor would have 4 steps per revolution. Dan?
But what if the top and the right were both to the north? You could do a half step. So
Well, that's something we could do, yes. If I had the electronics to do that, I could have south and south here, and north here. This guy would have to sit in the middle, wouldn't he? So if you wanted to make more complex stuff, you could do half stepping. And that would double the amount of resolution you've got. You'd have 8 steps per revolution. And if you really want to be tricky, you could put in, say for example, on this guy here and this guy here, they both have a magnetic field, but if I put in, say, 5 volts on this guy and 10 volts on this guy, this would have a stronger magnetic field than this one, and we'd end up not halfway in between, but more like 3/4 of the way. That's called microstepping.
Does that also work with pulse width modulation?
Pulse width modulation wouldn't do us much good here because of the problem of changing a magnetic field very quickly. We'll get into that later on. No, it's mostly just voltage or current amplitudes that we're worried about here. Now, microstepping is something that gets into the analog conversion thing, and your electronics are going to get very, very complicated then. As well, the finer the microstepping you do, the less accurate your microstepping will be. But these are all things you can do just by varying the coils, the polarity, what they're on. You can vary the amount of magnetic field you've got by varying the amount of current going through each of these guys. So you can do, in this particular arrangement, 4 steps per revolution, or with half stepping, 8 steps per revolution, or microstepping, a bunch of steps per revolution. It would depend on how you're microstepping. Any questions about that? Does that explain all those terms? Good. Okay. Let's talk about how strong this is.
Oh, sorry, I should have thrown a question in. Karl.
Sure.
You talked about 4-step motors and 8-step motors and 16s with all the mini parts. Can you get up to, as I bought, 200 and 400 step motors just by varying that voltage, or is there some more trick to those really high resolution steps?
Microstepping has nothing to do with the motor steps, the way it's constructed, that is. When it leaves the factory, if you build something like this, when it left the factory, the specifications would say 4 steps per revolution. That's it. And if you were tricky with electronics, you could do 8 steps per revolution by half-stepping, or more. But there are other tricks that we can get into later on as well. We're getting close to exactly that.
Okay,
but yes, that's when I'm going to talk more about construction. Right now I just want to get through the basics.
Okay.
So the next basic is, how strong is this going to be? What makes this motor strong? Well, for one thing, they can make them very strong because there's no tiny little brushes inside. You don't have to worry a lot about the bearings being far apart. When you bust open a stepper motor, it's always puzzling to people because they open it up and there's nothing inside except the thing that goes around. It looks like magic. Students would come to me and say, "Sir, I think I lost the pieces or something because it's just got this thing inside that goes around and there's no connections to it." Yeah, it is magic because this could be just a magnet with a hole drilled through it and an axle on it and it would work. No connection to it. So these things tend to last a long time. And they're easy to scale up as well. And they're very easy to scale down because there's no really complicated parts to it. How could we make it stronger? Well, you could put in bigger coils, or you could put in a bigger rotor, stuff like that. But if you just had a fixed motor, like Paul was asking, he bought a motor, and how many steps does it have? Well, if you buy a motor, how can you make it have more twisting power, more torque than it's already got? Basically, that's all a function of the magnetic field. You can't change how strong the rotor's magnetic field is because it's a permanent magnet. The only way you can change it is by damaging it, and there are ways to do that, but you can't really increase this. But you can increase the strength of the magnetic field. And since the resistance of these guys is determined by how much wire you've coiled up and how thick that wire is, that's fixed. You can't change that either. So basically the only thing you can change is the amount of current, because more current gives you more magnetic field. And the way you change that is by raising the voltage. So the short answer is, I want my motor to be more powerful, to have more torque. The short answer is, jack up the voltage. And that's about it. You will reach a limit. The limit will either be reached when A, you get saturation, that is to say this coil cannot produce any more magnetism because of its physical size, or B, you get the coil so hot that the insulation between the coils melt and it all becomes one big blob. And then it's not going to make any magnetic field anymore. So torque, given everything staying the same, can be changed or increased by increasing the voltage. Okay, now what Paul was asking is, how can we increase the steps? Well, I guess we could put in more coils, but that reaches a problem. There's only so many coils you can put in there, and really the coils are quite big. If you've ever taken a stepper motor apart, the coils are a large part of the motor itself. Well, here's a really nifty thing. Instead of using a bar magnet like we have, we're going to use something round. And we're going to do the absolute niftiest trick, and this is something you may not have noticed if you've taken a stepper motor apart. You may not have noticed that there are bumps. All the way around. Little splines. There are splines all the way around. And what they do on the motor itself is even trickier. They also have little splines on the motor. Rotor, pardon me. Thank you. And those little splines are actually where the magnets are. And they've got them oriented like that. And that's what those bumps, those splines are on the rotor. They're actually, those are the magnets. That's where the magnets are. Now, sorry?
So, obviously we don't have unipolar magnets. For each one of those bumps, where's the opposite end of the magnet?
I'm just drawing what you'd see on the outside.
Okay. So they're like pie-shaped slivers?
They're very, very small bars. They're actually, if you were to look at, I guess they'd be like this brush, long, thin, north, south, glued onto the round rotor.
Thank you.
You're welcome. Thanks for asking that. All right. And by the way, there are unipolar magnets. Physics says so. We just haven't found any yet. Look under the rug when you get home. What do I know? I've been working in this business for 35 years. I've never seen an electron either. So, why do they do this? Well, it's pretty obvious that if this coil is stretched over these three bumps, when this guy is south, these guys will all be south. And I'm not drawing it very well, but here's what I'm going to do. Let's clear some of this stuff up. Notice that this box is close to here, this box is close to here, and this box is close to here. I'm going to get rid of one of these guys. Like I said, I'm not drawing it very well. Now, if this guy is north, just like there are splines of magnets on the rotor, there are splines of magnets on the coil. Actually, they're just pieces of soft iron. And they become polarized in the direction of the coil. Now, as you can see, this little bar here is going to be polarized north, and he's going to attract the south splined magnets. And the same with this guy here. But what happens, and Paul, this is your answer, if right now this guy's north and these splines here are also north because they're close, they're attracting the south magnetic splines on the rotor, what happens if this guy becomes south?
It's going to turn really slightly.
This whole thing's going to turn really slightly. Instead of going kalunk like it did when it was a big fat bar magnet with only one pole,
It'll turn one position.
it'll turn one step. A very small step. That's small, or that step's smallness, resolution, is going to be determined by the spacing of the splines along the pole and the spacing of the permanent magnet splines on the rotor. So we're still following the same sequence. You know, south is going to be moving around like this, but instead of having one great big fat bar magnet with only one pole on it, those tiny splines are just going to move one spline's width, and that's why you're going to get smaller steps. If you ever want to know if you've ever got a mystery motor, I've got a couple here, and you want to know how many steps per revolution there are, you have to get your safe cracking sensitive pinkies out, and you have to go like this, mark at the start, and you can feel a little bump, 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 bumps, because this guy will have some residual magnetism as well. It's soft iron, and these guys are permanent magnets, and you can actually feel this thing go clunk, clunk, and you can just count the steps. So if you've got a mystery motor, you can count the steps, and you can know how many steps there will be. Half stepping will increase that, but you'll know how many steps it left the factory with. So that's pretty much it for the mechanical aspect of stepper motors. Anything I could go over?
Is your strength reduced the more number of steps you have if you're at the same voltage?
Strength, no. No.
Just because you're dealing with a smaller magnet.
Yeah, well,
that would be
no, the strength of a stepper motor is defined in 3 different ways. One's called pull in, that is to say, if you're not moving, if you're stopped and you want to do one step, how much torque can you actually get? And the other one is called pull out, and that's if you're moving, then how much torque can you actually get to stop it, to slow it down? And the third one is stall speed. You've got that sucker turn along, and at what? Stall torque. At what torque will it not actually move anymore? So there's 3 things, but they're all determined by the strength of these magnets, and that's very important because the stepper motors from 20 years ago are not as powerful or as small as the stepper motors now that we've got better magnetic material, and the size of these coils, and that's a small improvement, not much. Because even way back we were able to make very small coils. When you guys weren't born, I was using memory as very small coils. Anybody ever heard of core? Yep. We had tiny little ferrite cores with wire going through it that you couldn't see with the naked eye. So we could make small coils back then, but the magnets weren't so good. Now we've got better magnets. Here's another thing we could do to increase the number of steps. If each one of these green lines represents a permanent magnet to go clunk, clunk, clunk with, what you can also do is this. On the same rotor, you can have another set of permanent magnets offset to the center of them. And you do the same thing. That is to say, we have these bars, which are the electromagnets, running the length of the motor, so they'd be going this way. And now you can have this guy attracted by one of these. I'm only going to draw one. Or this guy, so you can offset the magnets a little bit even farther. So your machining isn't quite so fussy. You can just make the same thing and glue it together, offset a little bit. So there are some interesting tricks you can do, but this is all the mechanical parts of it. I'm only mentioning this so that you know how they work. That's all. You're not going to be fixing a stepper motor. Yes?
Is that what they mean when they refer to stacks?
Stacks, yes. Yes.
That'd be
2 stacks, that's correct. Yeah. You're not going to be fixing a stepper motor. If it doesn't work, you throw it away and get another one. Has anybody ever taken apart a stepper motor, put it back together again, and got it working? Neither have I. These things are pretty fussy. And they put those bearings in really hard. They're pressed in. It's hard to get these things apart. So if it breaks, you're in tough luck. And if you're in the service industry, I'll tell you this right now. If you've got a problem with the stepper motor, you probably don't. You probably have a problem with the electronics. In all my life, I have seen one stepper motor that died, ever. And that's only because every class I ever had in 30 years of teaching, I told everybody there, if you ever find a dead stepper motor, please let me know. Because I never did. So out of the thousands and thousands of students that I graduated, one of them brought me back a dead stepper motor. Has anybody ever seen old advertisements for a Heathkit robot called Hero? Yes, yes. Hero had an arm you could buy. They glued the arm on the back of its head for some reason, made it easier, I guess. And they had a little claw on it, and that claw was driven by a stepper motor, and it had a little plastic cover over top of it with holes in it. And I was in Chicago in 1986 talking to the guy who designed it. It was at a robot show. And I said, well, how'd this all work out? He says, oh, it worked out fine. It's standard stuff. We haven't had any problems, except we had people calling saying that the stepper motor is burning out. And that's not really a problem. I said, what? It's not really a problem? He says, yeah, because you see, when I designed it, I looked up, how hot it gets for the current that we're putting in the load and all that stuff and the speed and everything. And I knew it was going to get to somewhere around 150 degrees Celsius. That's why I put this plastic cover over it so nobody burns himself. I said, 150 degrees Celsius? He says, oh yeah, those things are rated to 180, no problem. Since there's so few moving parts, one, you can really spec these things to high temperatures. So they're quite sturdy, stepper motors are. They last forever. So mechanically, that's about all I've got to say here, unless you've got some questions. That's how they work inside, and that's how they're constructed, and they're tough little buggers.
So when you're installing a stepper motor, should you install it with a heatsink, or does it matter?
When you're installing a stepper motor, just bolt the thing on, that's all. Let me tell you, on a lot of equipment, you might have seen this on old printers, dot matrix printers, or even inkjet printers. Every time you turn it on, you hear this thing go, me. So you print, then you turn it off and on, you hear the same thing, me. What the hell is it doing? What it's doing is this. It doesn't know where the print head is when you turn it on. And it needs to find out. And it's got a stepper motor and a rubber band, moving this thing back and forth. Right? And what it does is they put a sensor at the right-hand part of or the left-hand part of the carriage, and when they power it up, they just turn that thing on for a while. If it takes 10 seconds to go from the far end to that end, they turn it on for 15 seconds. So that they know it's gone, yeah, bam. If they were clever, they'd put a sensor on it, so it would just go, me, and hit the sensor, go. Well, actually, they're really clever. They're so clever that they were too cheap to put a sensor in, and they just go, me. Stepper motors, they can take that all the time, no problem. So a lot of, you might even see a lot of robots do that.
Is there something that you don't want to do with a stepper motor?
Take it apart. Don't take them apart.
But I mean, overdriving it, running it too fast, and that kind of.
Now, if you try to run it too fast, it'll start missing steps, and it won't work. If you try to overdrive it, well, you probably could raise the voltage too high, and it might, as I said, burn the insulation out, get it too hot. But and you'd have to get it really hot.
Is there a way of determining how fast you can drive the motor?
If you've got a scrap motor, that's pretty tough. It's easy to tell how many steps is. You can feel them. It's easy to determine the windings, and I'll show you how later on. And it's not so hard to figure out how much current that they're rated for because you can measure the resistance of the coils. But as for just how hot you can get it, that's tough to figure out.
I have a question.
Yes.
With 2 stacks, you say that's a way of sort of, you still have only 4 coils typically, and that's a way of averaging out the magnetic field across the rotor?
No, it doesn't average it out. It just makes it so you got more points.
I see.
I didn't show it, but you'd also have to have more points on these guys now.
Sorry,
Yeah, on the head itself. Yeah, it's it gets a little intricate, but it's not complicated. It's just intricate. That's all. Stepper motors do all have a maximum speed, and here's the reason why. When we put current through a coil, you get a magnetic field. So if I just did this, something we do all the time. If I have a battery on this thing, and I have a switch. When I have the switch open, there is no magnetic field. I close the switch, current starts to flow from negative to positive, and I get a magnetic field. Now, here's the cool part. When I open the switch, the current has to stop flowing. But there's still a magnetic field out there. And what's happened is, there's this magnetic field perched on the coil, and you've just cut him off at the knees. But he's still there. And he's going to collapse. How did I get a magnetic field in the first place? I had electrons moving in a circuit. Now I've opened up the switch, the electrons stop, and the magnetic field begins to collapse. It now goes inwards. So now I have a coil of wire with a moving magnetic field. What's going to happen is it will generate voltage. Just like that. It's called back electromotive force, or reverse EMF. And how much voltage? Well, that depends on the amount of coils and how big the magnetic field was and how fast it's collapsing and all that stuff. But this is how we use this all the time. This is how we make transformers work, switch mode regulators work this way. 99% of all moving things work with something like this. Now, this is not a problem in this situation, and in fact, it can be a whole lot of fun. Here's what my uncles bought once when I was a little boy. They bought a book, and this book was a pretty thick book. You know, it's one of those books that has a big spline on it. You know, and it's got gold around it. You know, it's a very expensive looking book, right? And gold foil and everything. And I think it had some dull title on it, like Illustrated Sex Positions or something. And when you opened the thing, you found that it had a little catch on it, but it kind of had give to it. So eventually you spring this thing open, and what was inside was quite shocking. Because here's what they did. They had a switch which was connected to this coil of wire in this manner. This was connected to a spring. This isn't a coil, this is a physical spring, by the way. And so while it's closed, we had a magnetic field going. And that magnetic field actually was keeping the thing closed. But you could overpower it. And when you did that, you opened this up, and the spring would make this little switch go opening and closing it quite quickly. Well, what happened then is you get a magnetic field, and then the switch would open because it was going boing, And that magnetic field would collapse, and because there were so many coils in here, it would generate far more than the 1.5 volts that was on there, like about 300 volts. And the edges of this coil were connected to this gold filigree that was around the edge. And so when you finally open this thing, you were rewarded with this sproing noise, and the noise of some guy going, ah! Because he was getting 300 volts over and over and over again as this thing went. It was wonderful. I used to find out where my uncle would hide it, and I'd bring it down and show it to my friends. That's why I like electronics. Okay, what's the lesson there? If a book doesn't want to open it, don't open it. The lesson there is this: that magnetic field doesn't just evaporate when you stop the current. It is energy, and it's got to go somewhere. And so here's our problem. When you put current on this guy, plus and minus, it makes a magnetic field. And that's great. You can now move one step. But then you want to change it again, right? Because as soon as you move that step, you want to change the polarity. And so you've got a switch. It might be a FET, might be a transistor, but it opens up. And that magnetic field starts collapsing and creating a reverse voltage. And you're trying to pump in a reverse voltage, and it's trying to pump another voltage out. And that back EMF can be a problem. And in fact, that back EMF is what limits your maximum speed. That back EMF is what determines the maximum speed of rotation. Once you hit that point, you can't go any faster, no matter how many times or how fast you try to change the speed of rotation by changing the magnetic fields rotating around there. It won't change. So it's a long answer, but that's how you get to the maximum speed of a stepper motor. All right. Now I guess we're going to get into the electronics parts of how we switch this stuff and how we sense it. The first thing we're going to have to worry about is how they have arranged the coils. Now, just as I've got over here, in fact I'll use this. I have to repair it a bit. Okay, here's my other coil. Now, whenever this guy is south, what do you want this guy to be? If this guy's south, you'd want this guy to be... It would be more... It'd be clearer if I had my little bar magnet back. I'll put that guy back here. If this guy's south, he's attracting the north. Since this is a permanent magnet, this must be south. This guy must be north. Okay, good. And you can predict that. And the same thing over here. If this guy here were to become north, this guy would want to be south. You can predict that because this is a permanent magnet. And that means, since these two guys, the top ones and the other two, the horizontal ones, since they have to be a fixed polarity, it makes sense to just kind of tie them together. So here's what we're going to do. These are the vertical magnets. And these would be the horizontal magnets. It makes sense to do it that way because we know that when this guy's south, that guy's supposed to be north because the pole's got to be that way. So, if you're going to draw the schematic for this, here's what you end up with. The schematic representation would show, for the vertical coil, here's what you'd see. Because, electrically speaking, you have a wire which goes to a coil, and since he's connected to the end of this coil, they just become one coil. Electronically speaking, and the electrons can only see wire and coils, and all they see is that this coil is connected to that coil. So for the electron's point of view, there's just one coil, and that's the way we draw it. And the horizontal coil looks like this. So that's one way to build these things. Now the other way to build these things, and I'm just going to do a smaller version of this. So we've still got the same coils. We're just talking here about how the coils are connected internally. So here I've got all the wires brought out. Sometimes you'll actually see stepper motors that have 1, 2, 3, 4, 5, 6, 7, 8 wires coming out. Doesn't often happen, but sometimes you do. For this configuration, you'd only see 1, 2, 3, 4 wires coming out. Most of the time, they don't drag them all out. Instead, what they would do is this. They would say, well, you know, these two guys have to work together, so we've got to connect them together. But this is all we're going to do. We're going to give you one end to this guy, one end to this guy, and we're going to give you the middle end. And conversely, or perversely, for the other guys, we're going to give you this one, and these two guys here we're going to connect together. And that's what you're going to get. So you get 1, 2, 3, 4, 5, 6 wires coming out. Schematically, here's how these guys are drawn. You'd have, there's actually a couple of ways to draw them, but we'll just do it this way. It's the green ones, where's the red ones? Red ones, like this. So, from a schematic symbol point of view, you could have this as a motor, or you could have this as a motor. They still just got 4 coils in them. But what we're looking at is how they can be connected to the outside world. I have picked 2 motors out of our junk box here. And I have one that has 4 wires coming out of it. That would be this guy. I have another one which has 1, 2, 3, 4, 5, 6 wires coming out. That'd be this guy.
Is there an advantage to 4 versus 6?
Yes, indeed. And no, it depends. They're just different.
I love answers like that.
Well, the reason why these are like this has to do with construction, for one thing. The amount of flexibility you have in wiring up, it's not a big deal unless you're actually designing the electronics for it. And here's why it's a big deal. You remember way back, cast your minds back 20 minutes ago, when we had this little guy here? You remember this coil? what was really interesting about the electrons in this coil here? What do we do to this coil? Sometimes we had a.
Oh, it's bipolar.
It was a bipolar arrangement. Sometimes we had current going through this way to make one end north. Sometimes we had current going through the other way to make the other end south. And that's what we have to do to these guys here. Because sometimes I want this guy north, which means current got to go this way. Sometimes I want him south, which means current's got to go the other way. So all of these coils are bipolar. They have to have current flowing in different directions to get those different polarities of north and south, magnetic polarities. Now, if you've got this guy here, here's what you have to do. If you want this guy to be north, you'd have to have, we'll say, positive here and negative here. If you want him to be south, you've got to have negative here and positive here. And the same with this guy.
Sounds like a job for the H bridge.
It would be. It'd be a very good way to do that. The H bridge would be a way to change those polarities on it. How many transistors does the H bridge take?
You should all know this.
4. Good work. Yes. The H bridge takes 4. So you need an H bridge up here, and you need an H bridge up here. How many transistors would it take to drive this stepper motor? 8. Here's something very clever. On this guy here, because I have this connection, I can do something a little bit strange. I could have this guy here connect up to positive, and I can have this guy here connected to negative, and this guy here connected to, or sorry, wrong. My mistake here. Right now, there we go. So I connect this into ground, and if I put this to positive and this to negative, current's going to flow this way. Remember, rule number 1, current flows from negative to positive. Current is flowing from negative to ground because ground is more positive than negative. And current's flowing from ground to positive because ground is more negative than positive. Now, with this arrangement here, I can actually just change things a little bit differently. What happens if I put these guys to ground? And put this to positive? What's going to happen now?
Current flows down both sides.
Current flows this way. And now if I just put this guy to negative, what's going to happen now?
Goes the other way.
Current's going to go the other way. So now instead of having to switch two ends of something, I just have to switch one end. So it turns out that because of the clever ways you can set up the electronics, you can come out ahead by half the transistors on this method here. The name for these guys, this is called, no surprise, bipolar stepper motors and unipolar stepper motors. I don't know if you've heard that term before. So it's still the same four coils, and inside those coils are in the same place, just the way they've connected them. And If you've already got two power supplies, a positive and a negative, one makes sense. If you only have one power supply, well, the other one makes sense. So there isn't any advantage unless you have a particular situation which makes it to your advantage. All right, so now we got to the point where you can see where sometimes we might need a split polarity power supply, and sometimes we might need an H bridge, an H driver. Depends on your particular motor, or you might just want to pick the motor to suit the way you've got it. The advantages, well, with this you've got an H driver, which means you've got 8 transistors per motor, but you don't have to have 2 power supplies. If you're in a situation where you've already got 2 power supplies, you can save on transistors with this one. That's the only difference. I think that's about it. Unless anybody's got any questions specific to their own little inventions you want to work on. Yes? 5-wire. If you want to be really clever, you can tie these guys together. And so there's 8-wire, there's 6-wire, there's 5-wire. Also, sometimes you'll have 7-wire, where it's actually this guy right here, except that they've got a ground on the inside of the case that they bring out for some shielding reason or something. If you've got a stepper motor, the best thing to do is to make up yourself a little table of colors and get your ohm meter out and start measuring in between them. Most coils, with the cheap digital voltmeters we got around here, when you turn it to ohms, well, with just about every voltmeter in this whole place, if you turn it to ohms, 100 maximum, and you connect up your test leads, you'll measure 3 ohms right away, because the test leads have some resistance. So you're already screwed for accuracy. These guys here, they'll often measure somewhere between 1 to 100 ohms, depending on their size and their current rating and stuff like that. 10 ohms is not unusual. But if there's no connection, that'll be infinite ohms, and that's pretty easy to determine. So by making up a table and using a little common sense here, you can figure out how these guys are connected. My guess, because 2 of these wires are red, my guess right away is that that's these 2 wires here. And how can I tell which ones of the other colors they're connected to? By just using the ohm meter to measure between the 2. By measuring from here to here, I should get a reading. And by measuring from here to here, I should get half that reading, if my meter is accurate enough.
So with the 4-pin one or the 4-wire one, Dallas, you told about a trick where you can tie the 2 together and then try and turn the motor and it won't turn. And that will tell you the 2 that are on the same coil, right?
That's a way of doing it as well.
But is there any way of telling which side it is, or do you just have to...
By making that little table, you can't get away from that little table. You still have to draw them out a little bit and
Okay.
work on it. And that method, if it's a big motor, it'll work pretty well. If it's a small one, there might not be actual enough resistance to tell.
The other question is, I noticed that hooking the... if you hook leads up to a DC motor and turn it,
Yes.
you get a DC current. But if you hook leads up to this, you get an AC current.
That's correct. And it would make sense, wouldn't it? Because you've got a magnetic field, this guy here, moving through a coil, which always generates a current. But since we know there's splines, north, south, north, south, north, south, we've got a north field moving through this guy and then a south one. So your polarity would be positive and negative, and then negative and positive, which would be AC. If you got DC, then you've probably got you've got a DC motor probably.
Right.
Yes.
What are some of the suppression methods of back EMF with stepper motors that...
They're exactly the same as we covered with, it's a good thing to mention, as we covered with DC motors. Every one of these guys should have some kind of back EMF protection for that switch that I mentioned. Let me just draw one coil, and then we can figure that out.
No, you're not talking about the capacitor that you put across the DC motor, are you?
Well, no, I'm not. I'm actually talking about that problem with the magnetic field.
Right.
And here's the problem with that magnetic field. If I take a coil, a simple coil, and this happens with relays all the time. This is the most common, the quintessential, typical problem that novice people have with robotics. They put a relay in there. And then they connect that relay up to a transistor, if they're lucky. If they're unlucky, they connect it straight up to their Arduino, which keeps Arduino in business. Okay, rule number 3, the collector is connected to the load. Which one of these guys, top, bottom, is the collector?
The top.
Top. It's the collector. The emitter is the guy that has the arrow. Which way is the arrow pointing? Down or up? Look at rule number 2.
What's down?
Current flows
Into the pointy end.
into the pointy end. Now, rule number 1 says current flows from negative to positive. If current flows into the pointy end, then the pointy end must be this way. So now we know how to connect this transistor up. Now, transistors are switches. This guy's basically something like this. He is either an open or a closed switch, emitter to collector. Now, if we close him, you're going to get current flowing, and that current is going to produce a magnetic field. Now, if you remember back to that story of my uncle's in the golden-edged book, there was a 1.5 volt battery in there. How come they went, ah? Well, because when the magnetic field collapsed, it collapsed through a lot of coils of wire. And the number of coils determines the voltage you get out. And so there's a lot of coils in this relay. So when you close the switch, you get a magnetic field and the relay goes click, and your robot motor starts going. And then you tell your Arduino, okay, stop. And we open the switch and the current stops. But then the magnetic field collapses backwards and you get an awful lot of voltage. This now goes negative and this goes positive. 300 volts? Well, if you've used a little transistor that's only rated to switch 24 volts, it's not going to do it any good to have 300 volts across it. It won't work gooder. It will just go poof. And that's it. You'll say, oh, stupid cheap transistors. And you'll put another one in. And eventually, these guys, they put in great big ones to power a little teeny relay. So they got this transistor that's fully capable of handling all the current through the motor, but it's powering a relay instead. That doesn't cure all their problems, though. Notice we've got negative on this end. Well, that negative is a spike that may be 300 volts negative relative to ground, and it's going to go into the power supply, which goes everywhere, which also goes to your Arduino. And if you're really lucky, your Arduino is going to go, what was I doing? Reset. And you have the situation of, I don't understand it. The motor powers around, but every once in a while we turn off the motor and the Arduino resets. That's why. How do we cure that? Well, current flows from negative to positive. Boy, these rules are useful. Current flows into the pointy end. Negative to positive. Pointy end. If I put a diode across this guy here, what happens is every time this relay coil generates back EMF, reverse EMF, we just short the sucker back out again. And it doesn't go anywhere else except in here. It gets dissipated as heat in the end. So that same protection should be used on all transistors as well. You should make sure that that happens. If it's an H driver, you should have 4 of these cheap diodes. A 1N4000 and 1, 2, 3, 4, 5. That'll all work. And that takes care of this back EMF suppression. If you've got a properly built H driver, these things are already in there anyways. As well as they probably also got a little capacitor across there just to make sure nothing goes wrong. If you're really lucky, they're clever and they've got a diode in there backwards as well, just to make sure. And if you're really, really lucky and you spent a fair amount of money, what you've got here is a phototransistor, and your precious Arduino is actually connected up to an LED. So you're not even connected to that motor driver.
Optical isolation.
Yes, optical isolation. You could have a 12-volt battery running your motors and your 3-volt battery running your Arduino. They're only connected by a beam of light. It's hard to get voltage across a beam of light. Especially since inside these things, they put a thin sheet of mica. And they guarantee that even if you put 6,000 volts on this, it won't jump across the sheet of mica in there. So an optical isolator is always good. But still, don't forget, you've got to protect these guys too. Just because your Arduino's protected doesn't mean these guys won't fry you, so keep it all safe. If you just buy the motor driver, they've usually got all this stuff, and you just magically connect your Arduino up to it, and it works, and that's good. I think we covered that in the H drivers, but do it again. Does anybody have any projects with stepper motors that they need help? Yes, Dan.
Oh, would need help with?
Yeah.
But I built the CNC machine at home that uses stepper motors.
Uh-huh.
And I built a version of this printer robot, but I made the mistake of putting the steppers on the piece in the middle. I was hoping to just hang it off 2 nails.
Oh.
So it'd be more portable.
So it's got so much mass.
That's right. I tried to shave the weight down, but I haven't had time to get it right yet.
Okay. Helium balloons, maybe.
Oh.
Yes.
Got a heat wire.
Huh?
I need to figure out how to wire.
Oh, well, that's easy. You just make a table with the colors all the way across, and you put one in, or take one wire, start with white, and take your meter and see which one it's connected to, and just say 0 ohms between there, and then just go through all the possible connections, and it's done. 8 connections, 8 times 2, no more than 256 possibilities. Should be a piece of cake. Actually, once you get one, right, that reduces it. So.
128.
128.
Because they connected.
That's true. All right. So you guys feel confident you can build something with this now? Make a stepper motor work?
Well, I'm going to be writing a stepper motor driver, so I may have more questions for you later.
Well, actually, we could do that. And that's not a bad. It's not very long to go over it. When you think about it, you've got these coils, and what you have to do to them is power them up in different sequences, right? You've got to have a sequence B, C, D. And there's only 4 possible combinations for this, because there's only really, there may be a lot of steps, but that's done by having all those splines. There's really only 4 cycles you can go through. And so really what you want is you want to have this. For A, you want to have north and south. So if we're starting on the revolution here, we'd have these guys off and we'd have these guys on. Now, it depends how you want to connect them. And it depends what you've got driving them. But if I have an H driver driving them, Okay, here's an H driver, positive, negative. I'm going to connect this guy up to my H driver like so. And if you remember from the H driver, all we really have to have going into these guys after we've got a suitable decoder is either 0 equals clockwise, 1 equals counterclockwise, and clockwise would be positive here and negative here, counterclockwise would be negative here and positive here. So if you have an H driver driving it, you can reduce this down to 1 bit. The other thing you need to do is to worry about shutting it off. So you'd have to have an enable, and you'd have the standard classic this.
You're using the old slightly faded pens.
Oh, thank you. Okay. So clockwise, counterclockwise. For each H driver, this is the truth table you'd need. 1 bit would be enable, and the other bit would be direction. Doesn't matter which polarity you choose, but to turn these guys on at all, you'd need a 1 here. To change the polarity of these guys, you'd have to change this bit. If you have a 0 on the enable that's going into your H driver, it doesn't matter what the direction bit's doing, you don't have any current at all. It'd be like these guys here right now.
Sorry, is the enable bit a standard part of the H bridge? Or is
Yes,
it
it is.
Okay.
Yeah. It might say enable, or it might say bar or not enable, or it might say go or something like that. But enable and direction, there will always be 2 bits going into every H driver for that. Okay, so you can see that we have enable to start with, and then we have direction to change. So if we started here with south and north, these guys off, so in this particular, we'll start here, position 1. This particular situation, D and B have to be off. And A and C have to be, we'll say, from the H driver's point of view, in forward. Or, not forward, sorry, clockwise. If I want to push the motor rotor over here, this way, now I've got to have certain things done up for me. One is this. A and C have to be off. And B and D have to be on now. Let's call them clockwise. To get this to move over here, I have to turn B and D off. But now I have to have a north here and a south here, which is just the opposite of what I had in step number 1. So I'd have to have my motor driver feed out a counterclockwise. And that would get this guy here, like so. I'm keeping up here. For number 4, I've got to have this moved over to here, so that has to be north, that has to be south. These guys have to be off. A and C off. D and B have to be counterclockwise. And that's the table that you'd have to have for a complete rotation.
And then for half stepping,
Well, for half stepping, you'd have to have 8 times. You'd have to have, because you have 8 revolutions, you'd have to have 8 states. And you'd figure it out the same way.
so basically the next state would be like A and B both on, like A.
For half
clockwise, B
stepping?
clockwise,
Yeah, you'd have to have
So all
you'd
four
have
are
to
on
have
in that case.
all of them on, yes. But you'd have to be very careful about your polarities there. I think you got it.
Now, one thing that occurs to me, if you've got all of them on, you've got 4 coils energized, that's a stronger pull than just 2 coils energized. So do you have like an uneven torque by doing something like that?
No, you wouldn't have an uneven torque. Don't forget that you've got the rotor halfway between 2 poles,
Oh, right, okay.
and the distance is going to cause a problem. You're going to lose some torque there.
Right.
That would probably be the only thing I could think of, because your speed wouldn't matter a lot. Yeah, I wouldn't worry so much about half stepping, because usually stepper motors have hundreds of steps, and you don't have to gear them down. One of the great advantages about stepper motors is you always know how many steps you've gone, and you know exactly how far. And that's why printers loved to use them, especially to move the print head. They would just design the belts and the cogs and the diameter of the motor, the driver itself, so every step would mean 1 dot.
Oh, yes.
So if you go dot, 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 dot for every step, 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 step. If you tried to use a DC motor for that, then you had to have an encoder, that is a disc that had holes punched in it, and each hole represented the movement of a dot on the print head, and a light shining through it and a counter on it.
Actually, we disassembled at my place. We disassembled a fairly modern printer that had that, and a DC motor and a little disc with black stripes on it.
Yeah?
So maybe they're trying to go low cost or something. I
Uh,
assume that's cheaper than a stepper motor.
I don't know. I don't
It
know.
can spin faster.
It does spin faster, but there are some advantages to having feedback to it. With a stepper motor, if the paper was thick paper, or your ribbon was low and you crammed the head up against the ribbon to get some print out of it, the friction might cause you to lose a step, and you'd be lost not just that dot, but the whole rest of the page.
Right.
With a sensor on there, you know you've lost it. You increase the torque and just keep moving along. It's not a problem. I guess one last thing. I haven't covered them, but there's kind of a middle ground here. With a stepper motor, when you start up, you don't know where you are. And I went through that initialization sequence. Robots do the same thing. Sometimes you'll see a robot arm. You power it up, and this thing goes click, clunk, clunk, and it all contorts itself up till it's up against the
Finding
stops.
its end stops.
That's right, and then it goes doot, 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 and it knows where it is because it counts from where it is. With DC motors, you'd have to have encoders on each wheel, and the encoders would tell you where you are at any time. So you just power it up and read off the encoders, and you're done. Some cheap encoders are not absolute position encoders. They're just relative encoders. And they have to do the same thing. They either go to the stops where there's a sensor to tell them that there's a stop, or they stall it. Usually if it's a DC motor, they have sensors, though, or limit switches. There's something else which is an absolute position encoder, or an absolute position device, where you feed it a pulse width, and bang, it goes to that position. So if you've got 200 degrees of revolution on this thing, you feed it a 5 millisecond pulse width over and over and over again, it goes to there. You change that pulse width to 20 milliseconds, it goes to there. And that's an absolute encoder. We call those guys servos. Those are the radio-controlled servos that you have. You have to be careful which one you choose. I had a project recently where I had to use a radio-controlled servo simply because of the size, and they come all pre-equipped with gearing and everything. And this one had all kinds of sweet little digital programmable stuff in it. It was really neat. But it was an absolute position encoder. And the problem was I didn't know what position the actual device that was being driven would be in. It was basically two doors that opened up. I didn't know when they took this thing out of the package and put it on the wall, I didn't know where they would end up. And if I wanted this thing closed when I powered up, I couldn't close it gently upon initialization because I only had an absolute position. I could say 5 milliseconds, and if it was open all the way, this thing would go wah, and possibly crush somebody in between because this was very, very powerful. So it was quite difficult, and you couldn't just say, well, let's go 5 milliseconds, 6 milliseconds, because it might actually be closed already, in which case you'd open the damn thing real fast. So there was a bit of a problem with that. You had to put in switches, had this thing wake up, and you had to read where it was. And it took away a lot of the advantages of having the servo motor. So when you pick your motors, you have to decide what kind of encoders you want, how you're going to initialize them, stuff like that. That's it. Thank you very much for a great audience.